to the sixth lecture. Today we will discuss about the Euler's theorem and what does it state. So, we will write it instead of speaking it here. Now, this theorem is very important because you can see that if we are representing the rotation in terms of the psi theta phi, that is in terms of the Euler angles. So, that becomes an affair involved with the sine, cosine, all these trigonometric quantities. But if we want to eliminate these trigonometric quantities, so for that we have to look into the Euler parameters, and equivalently it is also called as the quaternions. But the Euler parameters and quaternions, they are strictly not the same, because the quaternions are developed from the complex notation, while the Euler parameters it is purely developed from the matrix notation. So, these two are totally different things, but they are equivalent, and quite often in literature they are used without any making any distinction. So, we continue with the Euler theorem. So, already we have looked into the rotation part. So, how the rotation is represented. Now, Euler theorem it states that, let us first look into one example. So, can we have camera here? So, see, we have earlier looked into that if this is a box and this I want to represent it like this, finally rotate in this way. So, this we have done in two ways, like giving one rotation like this and then one rotation like this, or either from here to here and then like this. Okay. Now, we can have very complex rotation. So, we have given some 3 rotations about the different axes, and finally, from one configuration, let us say we have come to this configuration. So, Euler theorem, what does it state? That there is an axis fixed in the body itself. So, this is a body and it is fixed in the body and also in the inertial space. So, if I say that this is a vector, my finger it is a vector in the inertial space, okay, and this is passing through this body, and this is also fixed in this body, and if I rotate this body about this axis, okay, this is fixed in the body, remember. So, this will my finger will pass through and it will be represented like this, this will go across this from inside. Okay. So, this axis is fixed both in the inertial space here also and in this body itself. So, in the body the axis it is not changing, okay. And if I rotate about this, let us say this axis is fixed like this, and if I rotate it like this. So, I can go to different orientation. So, these 3 rotations that we have given, it can be represented by a single rotation, which we call as the eigen axis rotation, and this is all about this is what the Euler theorem it states. So, let us write that theorem. The orientation of a rigid body from an initial one to a final one, means from initial one to a final one we are going by giving 3 rotation about the 3 different axes. Okay. So, this can be achieved by rotating body about an axis which is fixed in the body and in inertial frame as well. So, it is a fixed in the inertial frame or also fixed in the body and in the inertial frame as well. So, let us say that that fixed axis is here represented by some nu tilde or maybe we can represent this as E tilde. So, this is the fixed axis. Fixed axis in the body and inertial frame as well. Okay. So, if I give rotation and this is my body. Okay. So, if I rotate this body, let us say we make it 3 dimensional, something like this. So, if we rotate this body and say there is a vector going from this place to this place. Okay. So, this vector is E vector, this is fixed in the body and also in the inertial space, and this is a vector which is pointing to any particle in this body. Okay. So, as we rotate about this axis, we can see that this axis does not get affected, this will not rotate. So, this simply implies that if C is the matrix rotation which is indicating rotation about this eigen axis, then C times E tilde must be equal to lambda times E tilde. Means it is only showing that the E tilde vector which is not rotating, it can only get magnified by certain magnitude, but its direction is not changed. Okay. But here for C to be any rotation matrix, already we have looked into that it should satisfy certain properties, and we will look into that also here in this place. So, however, lambda need to be 1. Okay. However, lambda equal to 1. So, if this property is satisfied, then our job is done. So, let us state it formally. Or we call this as the eigen axis. Rotation matrix C, and lambda be the corresponding eigenvalue. Okay. So, here E tilde and lambda may be complex also. So, if it is so, then transpose we have to replace by Hermitian operator, or the we will replace this, let us write it this way, C tilde C operates on the E tilde, and if E tilde happens to be E tilde and lambda, they happen to be the complex one. So, in that case we will replace it by the Hermitian conjugate. That means, instead of writing C tilde transpose, we are writing it this way. This must be equal to, now this is operating on this E vector, and therefore, this is lambda E from the previous page what we have written, lambda E tilde So, this can be rearranged as from this place this will be, this is a scalar, it may be complex or it can be non complex. So, lambda star lambda times E tilde star E tilde. Okay. So, if this is a rotation matrix, so we must have this equal to I. If a rotation matrix, this is C, since E tilde star this is non-zero, so this quantity is non-zero, this vector, this is the eigen axis we are assuming, okay. Therefore, this will be non-zero, and this implies that 1 minus lambda star lambda will be equal to 0, and this implies lambda magnitude square, this will be equal to 1. Or lambda equal to lambda square magnitude we have written as equal to 1, and therefore, lambda magnitude equal to plus minus 1. But as we have discussed earlier that the minus 1, this eigenvector eigenvalue that we are getting, this will correspond to the left handed triad. So, we reject it. So, the minus part now, lambda equal to minus 1, this we are rejecting. Okay. So, with this lambda equal to plus 1, then we proceed. Now, as we stated that lambda for a rotation matrix, it is a fact that at least one value will be real, one eigenvalue will be real, and other two may be complex. If it so happens, so we can use the property of determinant of a matrix. Okay. C equal to C determinant, this will be equal to lambda 1 lambda 2 times lambda 3, and already we have looked into that one of the eigenvalue is 1. So, let us say, so this quantity is plus 1, and one of, because this is a rotation matrix. So, this must have, already we have looked into that this quantity should be plus 1. Thereafter, also we have lambda equal to plus 1, one of the eigenvalue. So, let us say lambda 1 is plus 1. So, we will have here 1, the other two are complex. So, complex conjugate. So, this will be E times j phi and E times they will be complex. So, we will represent this as E times j phi and E times plus j phi, and this will be equal to 1. Okay. So, this satisfies, obviously we can see that this is satisfied lambda 1, this is the property of the determinant of a matrix. Okay. And if we take the other two as the complex conjugate and one as the real one eigenvalue. So, we get this 1. So, this is satisfied. So, this implies that lambda 1 should be equal to 1, as we have rejected here this the minus part. So, this should be equal to plus 1, this quantity is plus 1, okay. Because the determinant of this will be representing as plus 1 for a rotation matrix. So, the eigenvalue also this must be plus 1. As already we have stated that we will reject it, because this will be not related to the right hand triad we are discussing about. Thus, what we see that C times E tilde, this equal to E tilde, means the vector E on which the matrix operates, it does not change that vector, it remains intact, means this becomes the eigen axis which is fixed in the body and also in the inertial space, and this is the rotation matrix corresponding to this eigen axis. Now, the question arises how to go about showing this C matrix, how the rotation matrix will be represented. So, that is another issue which will come to sometimes afterwards. Now, this rotation about the E tilde, rotation about E tilde will be given by using the properties of a matrix. So, we know that the trace of C means the sum of the diagonal elements, means C 11 plus C 22 plus C 33, this will be equal to lambda 1 plus lambda 2 plus lambda 3. This is the property of the trace of a matrix, where here in this case C is the rotation matrix, and C 11, C 22, C 33 are the diagonal elements, lambda 1, lambda 2, lambda 3, they are the eigenvalues. Okay. So, therefore, lambda 1 this equal to 1, this is e to the power j theta and plus e to the power minus phi and minus phi, where phi is the rotation angle. Okay. So, this can be written as 1 plus, we know that this quantity will be equal to cos phi. So, trace C, if we let us say indicate this by delta. So, this becomes delta equal to, and then the cos phi equal to delta minus 1 divided by 2, this gives you the rotation angle associated with matrix C. Okay. So, this is the angle by which the rotation matrix C will rotate about the eigen axis. So, you have given 3 general angular displacement. So, that will correspond to one single displacement of magnitude phi about the eigen axis E tilde. So, instead of using E tilde, later on we will continue with using A tilde, because it will be much more convenient to represent A tilde to, if we are converting into other frame. So, after the rotation of the frame, it can be represented as B tilde, and it is much simpler to work with. So, this is our phi is the rotation angle, this is the rotation angle. And later on we will look into that indeed this phi happens to be the rotation angle. But we need to prove that phi is indeed the rotation angle. Okay. So, without going into the details, let us consider that we have a matrix P. This means by definition, which we are defining as cos phi times I, where I is the identity matrix, one minus cos phi times A tilde times A tilde transpose minus sin phi times A tilde cross. As earlier defined, A tilde cross, this represents, this is the skew symmetric matrix, and this is your minus A 3, A 2, A 1, A 1 on this side, this will be minus A 2, and here this is A 3. So, this is your skew symmetric matrix. So, here right now we have taken it for granted that this is the combination which is representing matrix P, and we need to prove that this P is happens to be a rotation matrix which rotates about the eigen axis A tilde. This is the eigen axis. So, other way you can look into that if P is given, if your rotation matrix is given. So, how you will find phi, which is the rotation angle about the eigen axis and the eigen axis itself. Okay. Another way of looking into the same problem, that given this A tilde, which is the eigen axis, and rotation about that eigen axis by phi. So, get the value of get this matrix P. So, P is nothing but your C matrix that we have been representing. So, we will come to this right now we will use this P notation, because first we need to prove that P is indeed the rotation matrix. So, already we have looked into the rotation matrix properties. So, therefore, if this is representing rotation about the eigen axis by angle phi. So, therefore, this P matrix must satisfy the properties of the C matrix, where C transpose C times C transpose this equal to I, and also the determinant of C this equal to plus 1. So, this must be satisfied. So, if this matrix is satisfying these properties, then this will indeed be the rotation matrix, but we need to work it out. Okay. And obviously, whatever is represented here, this whole thing, it can be shown by a very simple geometric construction, that this is indeed a rotation about A tilde by angle phi, okay, which will come of course during course of time. Okay. So, first we need to prove that P transpose P equal to P P transpose equal to I. This is the first requirement that we have to do. So, P already we have assumed a particular form of P. So, P transpose P, this we can write as cos phi this whole transpose, and this is to be multiplied by see as we proceed. So, mathematics involved is very complex and very lengthy, and therefore, we cannot afford to do it in the this lecture class, and we will do the same as problems in the tutorial class. So, those some of the things will be said to you as problems, and you need to work out. If you are not able to do it, then the solution, you can look into the solution. Okay. So, taking the transpose of the first one, that gets reduced to cos phi I transpose equal to I 1 minus cos phi A tilde transpose. If you take transpose of this will give you A tilde transpose whole transpose times A tilde transpose. So, this becomes A tilde times A tilde transpose. So, it yields the same thing minus sin phi, this is a scalar. So, there is nothing to worry about, and A tilde cross transpose, this will be equal to, or we can write this as A tilde cross with minus sign, that you can check, because it is a skew symmetric matrix. So, if you take the transpose as on the previous page, if you take the transpose of this, the minus sign will appear here, here the plus sign will appear. So, and then if you take the minus sign, ultimately you will get the A cross itself. So, from there you can just look into this. This is very simple, and therefore, this is A cross transpose. So, we need to put here plus A tilde cross, and then this is to be multiplied by cos phi I cos phi minus sin phi times A tilde cross. And if you multiply and expand this, and few properties you need to use. So, first we have to expand it and then multiply, and the properties needs to be used is A tilde cross times A tilde, this will be equal to 0, and then A tilde transpose A tilde, this equal to 1, because we are assuming this A tilde magnitude to be equal to 1, which is a unit vector, and A tilde cross times A tilde cross, this will be equal to A tilde transpose times A tilde transpose minus I. So, here the first one is very simple, A tilde cross times A tilde. So, this simply implies that you have the skew symmetric matrix, this one here, and this you are operating by A tilde. And other way, if you look into the vector notation, so this is nothing but A cross A, and A cross A is obviously 0. So, either you do it this way or either do it this way, because this is giving you, this is the skew symmetric matrix operated on by this A vector, that gives you a vector, and also this gives you a vector, but this vector, of course, this turns out to be 0. This is very obvious, this is an inner product, and because this magnitude is 1. So, therefore, we get here 1, and this part, if you write these two skew symmetric matrix, like you have the A tilde cross, write the skew symmetric matrix for this, and A tilde cross, write skew symmetric matrix, take the product, and then if you simplify it and take the terms outside, break it into two parts. So, you will get this. So, this I will leave as a tutorial problem to do. So, this is your tutorial problem. Okay, some practice is required for it is good to do this practice. Okay, so, we have written earlier P transpose P or P P transpose, whatever way you write. So, P transpose P, you can expand it, and once you expand it, you will get this and cancel out the terms, you will get I, or either way, whatever way you work, or either you will start with P times here P transpose, okay, and the same thing you have to write the matrix here, this matrix and this matrix, the transpose, expand it and thereafter work out. So, if what we get there, this as the quantity as I. So, for you I will try to work out at least one of this. Okay. I will have to write the whole matrix here, only then we can proceed. So, this is P transpose P is equal to cos phi I A tilde times A tilde transpose minus. So, this becomes A tilde cross cos phi I So, one by one take the product here. So, if we take the product, the first term is cos square phi I. Okay. Similarly, the other terms we can multiply this with this. So, 1 minus cos phi times A tilde transpose A tilde times A tilde transpose, okay. And here this gives us minus sin square phi A tilde cross times A tilde cross. Okay. So, these are the corresponding three terms we have multiplied, then we need to do the cross term also. So, that will be cos phi times 1 minus cos phi times A tilde transpose, this term and this term. Similarly, this term needs to be multiplied by this one. So, this is sin phi times cos phi times A tilde cross. Okay. Thereafter, this term needs to be multiplied by this. So, that becomes 1 minus cos phi times cos phi A tilde times A tilde transpose, this one multiplied together, this we have already multiplied, the last one this remains. So, this comes with minus sin phi times 1 minus cos phi, okay, A tilde times A tilde transpose times A tilde cross. You have to take care of that, you are putting it in proper order, order should not be destroyed. Okay. So, lastly, we have to work with this one. So, this is sin phi times cos phi A tilde cross, okay. Multiplying this together that gives us plus sin phi times 1 minus cos phi A tilde cross times A tilde transpose. And the third term we have already multiplied, which is written here in this place. Now, the properties we have stated on the previous page, we can use them and shorten all these terms. So, this is cos square phi I, this term is 1, okay. A tilde transpose A tilde, this is 1. So, that we can write as, here we are missing this square term, this and this multiplied together, this is a square. So, 1 minus cos phi square A tilde times A tilde transpose. Okay. This already we have stated that this quantity is A tilde transpose minus I. So, we replace it by this particular one, and then we are left with this term. So, cos phi times 1 minus cos phi transpose A tilde cross. Okay. So, here we erase it. Because this term, this is sin phi cos phi A tilde cross. So, this term is with plus sign and this term is with minus sign. So, they will cancel out. So, we simply eliminate that term. Okay. There are few more terms which can be eliminated. So, we have noted till this extent cos phi 1 minus cos phi a tilde, this term goes, then plus 1 minus cos phi times cos phi, and then we have this term here, okay, minus sin phi 1 minus cos phi, sin phi, this is plus phi 1 minus cos phi, but we have to check whether these are cancelling or not. So, finally, we have minus sin phi times 1 minus cos phi. If we take this as common, so we will have here a tilde times a tilde transpose a tilde cross minus a tilde cross a tilde times a tilde transpose. So, if we work it out, okay, and we can show that this gets reduced to I. So, our job is done. Now, what we need to do, that we need to expand this term. Okay. So, obviously, this is a tenacious job and it is left to you at this stage that you prove that this quantity P transpose P, this equal to I, where you need to cancel out some of the terms by expanding this, by writing it in a proper format. And the basic mathematics involved, already I have stated you that use those properties to work it out. Okay. So, we stop it here and we will continue in the next lecture. And if you can work it out yourself, that will be a very big credit for you, because you need to put it in a proper format and this must turn out to be equal to I. So, this is one of the property that we are showing, that indeed this P matrix P transpose P and equal to, this will be P times P transpose, this will be equal to I. If we prove this, so one part is proved, the other part will remain. So, we continue in the next lecture. For the time being, thank you very much.